In this video, I will once again show you how to use the second derivative test to determine the intervals on which this function is either concave up, like this, or concave down, like this. But once we have answered this question, stay tuned for some bonus information, because we will go on to find the relative maxima and relative minima, inflection points, intervals of increasing and decreasing, and we will put it all together to find a lovely graph of this function. So in order to do the second derivative, first you must do the first derivative. So that's what we're going to do right now. F prime of x. Just kidding. First, we're going to slightly rewrite the original equation. I try to avoid any type of, what do they call it? The quotient rule. I try to avoid the quotient rule whenever I can. So I can easily rewrite this function as 6 times x squared plus 3 to the negative 1 power. Hopefully you can see that these would be equivalent. So now I can use the chain rule to find the derivative of this. Okay, so here comes my first derivative, f prime of x. The negative 1 comes to the front and makes this a negative 6. And we have to decrease the power by 1, so we will have the negative 2 power. The inner part remains unchanged for now, x squared plus 3. Okay, but we have this outer function, and that's what we just did. We did the derivative of the outer function, but now we have the inner function, x squared plus 3. So the chain rule says you have to multiply by the derivative of the inner function. So that's what I'm doing now. 2x. The derivative of x squared plus 3 is simply 2x because of the power rule. So that's it. This is an expression for the first derivative. I will clean this up a little bit. So f prime of x equals the negative 6 times the 2x will become a negative 12x. And then because of the negative 2 power, this expression will drop down to the denominator and become x squared plus 3 to the second power. So this is my expression for the derivative. Don't forget that the derivative tells you where the function is increasing and where it is decreasing. All right, that's what the first derivative test tells us. Now, we will not need the critical numbers for the concave upward and concave downward question, but for the bonus material, we will. So I'm going to go ahead and find the critical values from the first derivative. For the critical numbers, we need to know where the first derivative is equal to 0. And we also need to know where the first derivative is undefined. Very interesting. So if you want to set a fraction equal to 0, really all you have to do is set the numerator equal to 0, because the denominator can never be 0. That would be undefined. So if f prime of x is ever going to equal 0, it will have to be where negative 12x is equal to 0. Dividing both sides by negative 12, we get x equals 0. And that would be a critical number. Now, where is f prime of x undefined? Well, it's going to be undefined where the denominator is equal to 0. So if we set x squared plus 3 squared equal to 0, any solutions to this will be undefined. However, you should be able to tell right now that there will be no solutions here. Because look, we're squaring this whole thing. And, well, okay, you could get 0 from that. I'm being too quick. If you took the square root of both sides, we'll look at it that way, that would give us x squared plus 3 is equal to 0. If you subtract 3 from both sides, that will give you x squared is equal to negative 3. All right, so maybe this is the point where we can boldly declare that there will be no solutions here. You can't square something and get a negative number out of it. Or I guess you could say if we tried to take the square root of both sides, we get imaginary numbers. So there are no real solutions here. So x equals 0 is our only critical number. But like I said, we didn't even really need that for the concavity question. So let's move on to the second derivative. I would love to take the derivative of this derivative, but again, I really do not want to do the quotient rule. So I'm going to avoid that once again by rewriting this using negative exponents. So this would be the same thing as having negative 12x times, and I'm going to do the x squared plus 3 to the negative 2 power. The negative 2 power would drop me right down to the denominator. This would be the same thing. But in this form, I can use the product rule. So when I find the derivative, according to the product rule, first you take the derivative of the first factor. So the derivative of negative 12x is negative 12. So I will start off with a negative 12. And then you multiply by the second factor, which you do not change. So I'm going to keep my x squared plus 3 to the negative 2 power. Okay? And then you add, and then you switch. So the second time around, I'm going to leave the first factor alone. So I'm going to have my negative 12x. But I'm going to take the derivative of the second factor this time. I hope you can see that I'm going to have to use the chain rule because I have this function inside of a function. If I first do the derivative of the outer function, the negative 2 will go in the front, and I will have to reduce the power by 1. So the outer function will become negative 2 times stuff to the negative 3 power. Okay, see how I move the negative 2 to the front and I reduce the power by 1. The inner function stays the same for this part of it, so I keep my x squared plus 3. But please don't forget, for the chain rule, we then have to multiply by the derivative of the inner function. The derivative of x squared plus 3 is simply 2x. All right, quick power rule, derivative of a constant is 0. So this is an expression for the second derivative. Let's just clean it up as much as we can. So I'm going to have f double prime of x equals, and let's see, I think I'll leave this alone for right now. Negative 12x squared plus 3 to the negative 2 power. What are my signs doing over here? A negative times a negative is a positive. Okay, times another 2. So 12 times 2 is 24, times 2 is 48. So I'm going to have a positive 48. And then I have x and another x, so that'll be x squared. And then the parentheses, x squared plus 3 to the negative 3 power. I think it is time to rewrite this in fraction form without the negative exponents. So if I do that, I will have f double prime of x equals, okay, this part is going to drop down, so I'm going to end up with negative 12 over x squared plus 3 to the positive 2 power. All right, similarly, the 48x squared will be in the numerator. And this part will end up in the denominator because of the negative power. So I will have x squared plus 3 cubed. All right, I really need to combine these together. So in order to add fractions, of course you need like denominators. So I see that both involve x squared plus 3. It's just that this one's to the second power and this one's to the third power. So all I need is one more factor of x squared plus 3 to make this into the third power. If we multiply the numerator and denominator by an extra x squared plus 3, hopefully you can see that the denominator will become x squared plus 3 cubed, right? Because I'm just multiplying by just an extra factor. Now there's 3 of them, so it'll be cubed. So now I have like denominators. So I'm going to go ahead and add the numerators. I think I'm going to do 2 steps at once. I think you can handle it. We've got the like denominators now, so I'm going to go ahead and keep my like denominator of x squared plus 3 squared, cubed that I just made. I'm going to distribute the negative 12, and I'm going to go ahead and add the 48x squared onto the end of it. So distributing here, I'm going to get negative 12x squared minus 36, and then I'll have the plus 48x squared happening. Let's go ahead and combine these like terms. So I'm going to end up with f double prime equals 36x squared minus 36 over x squared plus 3 cubed. You know what, just for fun, I think I will factor out the GCF. I think that it will make it easier for me to evaluate later. So I'm going to write 36 times x squared minus 1. Okay, over x squared plus 3 cubed. All right, we did it. Okay, that was a long one in terms of finding the second derivative. But let's not forget the point. We need to find the critical numbers for the second derivative so that we can use the second derivative test like on a number line. So critical numbers, we need to know where the second derivative is equal to 0, because that will be one source of critical numbers. And we also need to know where the second derivative is undefined. That's another source of critical numbers. And once again, when you have a fraction that you're trying to set equal to 0, you can really just set the numerator equal to 0. The denominator can't be 0, only the numerator can equal 0. So 36 times x squared minus 1 equals 0. That's the only way the second derivative will ever equal 0. Dividing both sides by 36, we have x squared minus 1 is equal to 0. I guess you can either factor it or add and take the square root. I think I'll factor this time. So I've got x plus 1 times x minus 1 is equal to 0. So by the zero product property, we have x equals negative 1. That's a critical number. And we have x equals positive 1. That's a critical number. Now, where will the second derivative be undefined? Well, that'll happen when the denominator is equal to 0. All right, because the denominator is not allowed to be 0. If I take the cube root of both sides, that's going to give me x squared plus 3 is equal to 0. Subtracting 3 from both sides, this is looking really familiar. And once again, you can't square something and get a negative number. So there will be no solutions here. So these two numbers, negative 1 and positive 1, are the only critical numbers. Let's go ahead and set up our number line and use the second derivative test. Okay, so -1 and +1. So here's -1, and here is +1. I am going to put a little second derivative down here, like a label, to remind us that any calculations we do down here will be second derivative evaluations. So we need to pick a value in each interval. Okay, so I'm going to pick a value right here, a value of -2. And I'm going to pick a value in this interval. I'm switching colors. I'm going to pick 0. And then I'm going to pick a value in this interval, and I'm going to pick 2. Okay, so let's evaluate the second derivative at each of these three numbers. All I care about is whether they are positive or negative. So if I get an opportunity to stop evaluating and just put a plus or a minus, I'll do that. I copied down the second derivative right here so we can just remember what it looks like without scrolling up. So let's evaluate at -2. So we will have 36 times -2 squared minus 1 over -2 squared plus 3 cubed. All right, so that'll be 36 times 4 minus 1, okay, over 4 plus 3 cubed. So obviously, 4 minus 1 is 3. So in the numerator, it's going to be a positive result. And in the denominator, it's going to also be a positive result. So a positive divided by a positive is a positive. Okay, so when the second derivative is positive, that tells you that the graph is going to be concave up in that particular interval. So let's keep going. How about at 0? So we will have 36 times 0 squared minus 1 over 0 squared plus 3 to the third power. So this will be 36 times -1, right? The 0 just kind of goes away, over, and this will just be 3 to the third power, so this will just be 27. So we're going to have a positive, 36 times -1 is a negative. So we're going to have a negative divided by a positive. So that is going to be a negative result, which means that the graph will be concave down in this interval. And finally, let's check what happens at +2. So that would be 36 times 2 squared minus 1 over 2 squared plus 3 cubed. Let me go ahead and erase this because it just might get in my way. All right, so this is going to be 36 times 4 minus 1, so it's 36 times 3 over, and this is 4 plus 3, so that's going to be 7 to the third power. So I've got a positive divided by a positive, which of course is a positive. When the second derivative is positive, that means the function, the graph, is going to be concave up in that interval. So we are ready to answer the question. So the function will be concave up from negative infinity to negative 1, and from 1 to positive infinity, and concave down from negative 1 to positive 1. Let's just write that down. And this is the final answer. We found the intervals on which the function is concave up and the intervals where it is concave down. So this is the point where I'm going to tack on some bonus material. So if you stay with me, I'm going to layer on what we know about the first derivative, and we're going to do the first derivative test and find where the function is increasing and decreasing. We're going to find the relative maxima and the inflection points. Speaking of points of inflection, we don't need the first derivative for that. We can go ahead and talk about that right now. Remember that a point of inflection is where the graph goes from concave up to concave down, or from concave down to concave up. So we can see that there will be a point of inflection at negative 1. So negative 1 comma something will be a point of inflection. Let's find the y value that goes with it. So remember, this is what the original function looked like, 6 over x squared plus 3. Evaluating at negative 1, this is going to become 6 over negative 1 squared plus 3. So that'll be positive 1 plus 3, so that'll be 6 over 4, which is 3 halves. So negative 1 comma 3 over 2. Okay, reset, reset. We have another point of inflection here at positive 1. So we know it'll be 1 comma something. And again, we will evaluate. So it would be just 1 squared plus 3. Because of the even power, this is going to have the same value as it did last time. So this will again be 6 over 4, which is 3 over 2. So 1 comma 3 over 2 is a second point of inflection. Now it's time to do the first derivative test, and I need you to remember two things. First of all, the first derivative was negative 12x over x squared plus 3 squared. Keep that in your mind. And also, the critical number was x equals 0 regarding the first derivative. I'm going to mark the top half of my graph with f prime to remind me that any calculations I do up here will be an evaluation of the first derivative. So remember that the critical number is 0. That was the only one. So I'm going to go ahead and put a mark here. So I'm going to go ahead and put a 0 on this side, all right, because I'm doing my calculations up here now. So that's my critical number. So ignore the negative 1 and the positive 1. I only have 2 intervals. So in fact, I think I will use the negative 1 as a test value. So I'm going to put a little negative 1 in color, okay, and I'm going to use a positive 1. Okay, so these colored numbers are going to be my test values. So I copied down the first derivative, so we wouldn't have to hold it in our minds the entire time or scroll back and forth. So let's evaluate at these two numbers. So in the first interval, I'm going to have negative 12 times negative 1 over negative 1 squared plus 3 squared. Okay, so that is going to be, well, all I need to know is will it be positive or negative. So obviously in the numerator, a negative times negative is a positive. In the denominator, I'm going to have a positive 1 plus 3. So I'm going to get a positive number down here. So in this interval, the first derivative is going to be positive. So that means that in this interval, which goes all the way from negative infinity to 0, there are only two intervals on this side of the graph. The graph is going to be increasing. So it's going to be increasing from negative infinity to 0. Okay, first derivative test. Now let's do let's evaluate the first derivative at 1 for the second interval. So I'm going to have negative 12 times 1 over 1 squared plus 3 squared. So I'm going to have a negative number in the numerator this time, but the denominator is still all positive. But that does mean that the net result is going to be a negative value. So that means in this interval, the graph should be decreasing. So from 0 to infinity, the graph is decreasing. So in addition to the points of inflection that we found, we should also be able to find a relative max right here. So there should be a relative max. I'm running out of space down there, so I'm going to evaluate up here. So here's the original function, and we know that the x value is 0 for my relative max. So if I substitute 0 right here, that's going to give me f of x is equal to 6 over 3, which is simply 2. Okay, so my relative max should be at the point 0, 2. So armed with this gold mine of information, let's attempt a sketch of the graph. All right, so we know where the function is increasing and decreasing. We know where it's concave up and concave down. We have a relative max and we have 2 points of inflection. Let's combine all of that into a graph. So here is the relative max and the 2 points of inflection that we were just talking about. When I do my graphs, I usually like to do my concavity first, and then I worry about increasing and decreasing later, because sometimes the concavity takes care of the increasing and decreasing. So, for example, we see that the graph should be concave down between -1 and +1. Okay, so we know that at -1 we're here and +1 we're here. So you can already kind of see it happening concave down between those 2 points. Beyond those points, the graph should be concave up, all right? From negative infinity to -1, and from 1 to positive infinity, it should be concave up. So that's why in these intervals, the graph should be bending upward like this. Okay? So that's the idea. Let's look back and make sure this matches what we know about increasing and decreasing intervals. So the graph should be increasing from negative infinity to 0 and decreasing from 0 to positive infinity. So you can see that is what's happening. From negative infinity to 0, the graph is rising. All right, it might switch from concave up to concave down, but it is rising the entire time. And then from 0 to infinity, the graph is falling the entire time. It is decreasing. So this graph matches all of the information that we gathered. Let's finish this off with a quick glance at the real graph. So as you can see, the actual graph matches up perfectly with what we predicted. We've got the relative max here at 0, 2. And you can see right here at 1, 3 over 2, this is where the inflection would be. and -1, 3/2, another point of inflection. All right, we've got the concave up, changing subtly to concave down, and then subtly again changing back to concave up, increasing on the left and decreasing on the right.